All right, so what the goal is for tonight is to consolidate some of the info that we've learned in 4.4 and 4.5 because the processes that we've gone over in this section, in these two sections, are actually very similar, and it helps to step back and look at the big picture. So let's take a look at the whole process for finding real or imaginary zeros, because a lot of times people don't always see the commonality between the processes. First, what we start out with is we have an unfactored polynomial. Okay? When we say it's unfactored, what we don't know, UNK is unknown, zeros and factors. We don't know either of those things. So we have something that's, x to the fourth plus some number times x cubed plus blah, 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 blah. Okay? It doesn't have to be fourth order. I just pulled that out of the air. Okay. The first step we want to use, or the first thing we want to try, is we want to take advantage of any given zeros. So are there any zeros that we are given right off? You may remember that several of our problems that we worked on, we wound up having a couple of zeros given to us, usually in terms of complex zeros. If you have a complex zero that's given to you, you want to get the conjugate, okay, because that gives you 2 for the price of 1. If they give you a plus bi, then you know automatically that a minus bi is going to be a zero of that polynomial. The same thing holds if you're given a minus bi and you need a plus bi. All right. Well, let's say either we've exhausted our list of given zeros or we simply are not given any at all. In that case, our next step is to use the rational zero theorem to find a list. We get a list of our possible zeros, and we confirm these with the graph on the calculator. Okay? When we confirm these, what we do is we say, okay, well, is our function actually equal to 0 at that point? So we plug in, we use the calculating function or the calculating menu on the graph utility, and we can go ahead and see if it's actually equal to 0 there to test it out. Now that we've done that, what you're going to get is you're going to get a list of numbers. You're going to get a list of zeros that you know are zeros of that function. Okay, it's going to look like x is equal to blah, 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 are zeros. Okay, well, if you have a list of zeros, then basically you can set it up as factored with the zeros that you know. Okay, and if some of your zeros are imaginary, that's fine. So it might look something like this. F of x is equal to x minus one number, x minus another number, and so on and so forth. So here's an example of that. I'm just going to give you some values. You might have f of x is equal to x minus 2, for example. That's a real zero at x is equal to 2. X plus 3i. Because we know 3 or negative 3i would be a 0, so would positive 3i, so x minus 3i, and maybe a couple more after that if you have more than a third order polynomial. Okay, now it's possible you may be done there. If you have four linear factors and it's a fourth order polynomial, you're good. But if you're not, then you still have a couple more steps. So if you still have unknown factors, now we need to divide. You have to divide the known factors in. Now there's two ways of doing this. If you have real zeros, if you have a real zero, for example, in this above example that where I just wrote these in, this x minus 2 term, I'm going to go ahead and highlight it. This x minus 2 right here, that's a real zero. When you divide that in, the easiest thing to do is going to be to use synthetic division. The x minus 2, that's a 0 at x is equal to 2. The fastest thing to do, synthetic division. Do you have to use synthetic division? No. Is it easier? Yeah. Okay, the other option is that you have a non-real zero, or if you have an imaginary or a complex zero. Okay, now if you have complex zeros, you're not going to have just one. You're going to have, for example, they're complex conjugates. They're going to be coming in pairs. So here, use the highlighter again, use the green this time. This x plus 3i and x minus 3i. That gives us two zeros, one at positive 3i, the other one at negative 3i. Now, when we divide those in, we do not have a quick technique for being able to divide an imaginary zero into a bunch of real coefficients. So, i.e. the x minus 3i times the x plus 3i above. Okay, what you want to do is you want to multiply the conjugate zeros to make all real. And then divide in. Now, when you multiply those two, you are not going to get a linear factor. You're going to get, for example, these two guys, you're going to get x squared plus 9. So what you would have to do is you would have to actually use long division. So your hand is kind of forced. You have to use long division. It'd be really nice if we could use synthetic division, but unfortunately, since those don't give us linear factors, our hands are tied. Okay, now, if we scroll back up, this function right here could be x minus 2 times x plus 3i times x minus 3i, and then we could have something else that we don't know, okay? This is three linear factors, the x minus 2, x plus 3i, x minus 3i. If it's a fourth order or a fifth order polynomial, we have something left there that we still have to deal with. So those question marks that you don't know what they are, you have to deal with that on its own. Okay, sometimes you get left with something you can factor by hand, but to be honest with you, if you've already found all the real zeros, chances are it's going to be a quadratic, and it'd be really nice if you could factor it, but usually what you wind up having to do is use the quadratic formula to be able to find out what x values would make that last thing equal to 0. That's going to give you that, and you list it out. F of x is equal to x minus your first 0, x minus your next 0, and so on and so forth once you have them all done. And you're finished. So let's try out an example where we are just given an unfactored polynomial and deal with it all the way through. Here's my function. F of x is equal to x to the fourth minus 7x cubed plus 14x squared plus 2x minus 20. Okay, first things first, are we given any zeros? The answer is no. So the next thing we need to try is use the rational zeros theorem. Rational zeros theorem, possible zeros, x is equal to plus or minus factors of 20. Those are going to be 1, 2, 4, 5, 10, and 20. All over factors of 1, because that's our leading coefficient, 1. So we actually wind up with a list that's not all that long. 1, 2, 4, 5, 10, and 20. All right, so next up, we need to confirm those on our calculator. Now, in the interest of time, well, I thought I had it in there, but I don't. So let's plug it in. X to the fourth minus 7x cubed plus 14x squared plus 2x minus 20. Graph it. And as you can see, it looks like we have a couple of zeros there at here at -1, here at +2. Now, our window, though, only goes from -10 to 10. So just in case this 20 is one of our zeros, what I'm going to do is I'm going to expand my window out a little bit. I'm going to do my window from -25 to 25 just to make sure that all my possible zeros are covered. And that concern turned out to be unfounded. I only have these possible zeros here. It looks like at -1 and 2. Just to make sure, test out my value. X is equal to -1. Y is equal to 0. So -1 is a 0. And at 2, and 2 is a 0. So X equals -1 and 2 check out. Everything else is trash. So what I have here is I have a function that, because I have a 0 at -1, I know x plus 1 is a factor. And because I have a 0 at -2, or at 2, I know x minus 2 is a factor. And I have something out here that's going to be second order, because x, I have one x right here, another x right here, and so I need 2 more in order to make an x to the fourth. All right. I do not have any imaginary zeros that are given to me, so I don't need to multiply these guys together. I just have real zeros right here. So the fastest and easiest way to do that is use synthetic division. So let's go ahead and do that. I'm going to do the 2 first. So 2 going into x to the fourth minus 7x cubed plus 14x squared plus 2x minus 20. Now, I know this is a 0, my polynomial, so if I get a remainder, that means I goobered something up. I'm going to work through this real fast. All right, so this leaves us x cubed minus 5x squared plus 4x plus 10. All right, now we need to divide that -1, this, into what's left. So I have a -1 going into the 1, minus 5, 4, and 10. I'll work through this real fast. Okay, so what I'm left with is x to the fourth minus 6x plus 10. That is what is left after I factor out those two. So I have an intermediate step, or intermediate stage, of x minus 2 times x plus 1. Actually, upstairs just a little bit, I did x plus 1 times x minus 2. So I'm going to stick with that order. Doesn't really matter, but just to keep things consistent. Ooh. That's a mistake. That's supposed to be an x squared minus 6x. X squared minus 6x plus 10. Okay, x squared minus 6x plus 10. We need to factor that somehow. It would be absolutely magical if I could factor that and get real numbers, but unfortunately I cannot. So what I'm left doing is I need to find out when that's equal to 0 by another means, which is the quadratic formula. So b is negative 6, c is 10, a is 1. So let's plug in and crank. X equals negative b plus or minus the square root b squared minus 4 times a times c all over 2 times a, which is 2 times 1. Simplify this real fast. 6 plus or minus square root 36 minus 40 is negative 4 over 2. That is 6 plus or minus 2i all over 2. That leaves me with 3 plus or minus I. Okay, so those are my last two zeros at x is equal to 3 plus or minus I. So finally, to write this out all the way, I have x plus 1, my first zero, x minus 2 with my second zero at x is equal to 2, and then I have the 3 plus or minus I. So x minus 3 plus I, x minus 3 minus I. And we're done. Okay, so I paused there for a sec to check out our practice problems, and they are this. They are at the end of section 4.5. They are on page 388. Numbers 29 through 31. So that's 3 problems. Go through this process. Sometimes you might wind up with an imaginary 0 that you have to multiply before you factor in. Other times you'll wind up with a problem like what we just did, where you can just get through with synthetic division and then the quadratic formula. Good luck, and I'll see you in class.